Today we're going to take a look at section 11.7, which is cylindrical and spherical coordinates. We're going to start with cylindrical. And it works like this. The cylindrical coordinate system in this system we have a point P, and it is represented by r theta z, and the r theta is a polar representation of the projection of P in the xy plane. And then z is the same thing it is in rectangular coordinate system. No, that's not a z. It's supposed to be a 2. Goodness. Z is the directed distance from r theta to the point P. So it's the vertical distance. So if you measured very much like we did with polar coordinates, r is the distance away from the origin, out toward the positive x-axis. Theta is the distance around the circle measured from the positive x-axis. And then if you went straight up in the air, right, that's your z coordinate, just like it would be in the xy, and just like in the rectangular coordinate system. Easy enough? Okay, so the formulas should look very familiar because they feel a lot like the polar coordinate system. So when we're going from cylindrical to rectangular, in fact, we have x equals r cosine theta, y equals r sine theta. All of that's exactly the same. And z is z. It's exciting, right? Same thing. Going the other direction, rectangular to cylindrical. Also mirror the ones we did before. We have x squared plus y squared equals r squared. And we have the tangent of theta equals y over x. And once again, z equals z. So it's just this three-dimensionalized extension of the polar coordinate system. So we need a couple of conversions, more than a couple maybe, but a few. So the first one is we're going to convert cylindrical to rectangular. And our cylindrical coordinate that we have is 6, negative pi over 4, 2. So one of these is very directly easy. It's the z, 2, right? So this will automatically become something with a 2 on the end because z stays the same. The other conversions will feel just like what we did in polar coordinate system. How do we find x? How do we find y? Well, x is r cosine theta. Well, r is 6, and theta is negative pi over 4. So what is the cosine? You might want to grab a calculator or a unit circle perspective in your head anyway. What is the cosine of negative pi over 4?
square root 2 over 2.
Yeah, it is. So we have 6, we have square root 2 over 2. This ends up giving us 3 square roots of 2. So we have 3 square root 2 for x. Very similarly, y is r, say 6 sine of negative pi over 4. So what is the sine value at negative pi over 4? Close? With negative, yeah. So we're in the fourth quadrant if we're thinking two-dimensional. So negative square root 2 over 2. So this would be negative 3 square root 2. Okay, easy enough?
Sure.
It's really not much different than we've done, right? Let's go backwards just to say that we have. So we're going to go from, I'm going to kind of abbreviate the directions. We're going to go from rectangular to cylindrical. It is important that you pay attention to the descriptions because there are some cases where you cannot just by glance know, oh, this is really a cylindrical coordinate, or this is really a rectangular coordinate, or in a moment here, this is really a spherical coordinate. There is some overlap where sometimes it's not entirely obvious. Sometimes it is pretty obvious, but sometimes it's not. So do pay attention to what they're giving you as what kind of system you're already in. This one is 3, negative 3, and 7. So once again, we get one of them for free. 7, right? So finding the r value, we have x squared plus y squared equals r squared. And my x squared, or x is 3, so this is 3 squared. And then I have negative 3 squared equals r squared. So if we simplify a little bit, add some pieces, square, well, not in that order, square some things, add some pieces, and then take a square root. What do we get for r?
3 square root 2.
Mm-hmm. And we actually get a plus or a minus, right? We have some choice. I mean, we don't have to let it be one or the other. We get to pick. Probably your default's going to let it to be the positive part of it, but you wouldn't have to. I'm going to call it 3 square root 2. You might say, well, how do I know which one to pick? Well, it usually just depends on whichever one you pick is going to affect what the angle is that you're choosing to go along with it. So once you've picked one, you have to figure out the other one that corresponds appropriately. Using the r value being positive is often a nice choice. Tangent of theta is y over x. So this is the tangent of theta is equal to what? Yeah, negative 1, because I have negative 3 and positive 3. So my theta value, or if I do either think of it as an inverse tangent, or you can do it as a unit circle directly thinking about it that way. But where do I have a tangent value that is negative 1?
3 pi over 4
Okay, so that's one of them.
and 7 pi over 4.
And you could also represent it, you're looking at a unit circle from the perspective that we normally draw it. You could also think of it from the perspective that you're going backwards and it's negative pi over 4, right? So how do we decide which one of those values goes with 3 square root 2? Well, we want to think about this like the two-dimensional projection if we project it down into the xy plane. How do we do that? Well, we just look at the x and the y coordinates that we have in our rectangular coordinate system. If I'm thinking in the rectangular coordinate system's xy plane, what quadrant am I in if I'm at 3, negative 3? Annika, 4. We're in quadrant 4. So quadrant 4 would be, we're at roughly here, right? So we're in quadrant 4. So if I've gone a positive 3 square root 2 out, then I would either, in order to get to that point, so I've gone out to, say here, somewhere in here, I don't know, somewhere over here. I either want to go backwards, and I can go the negative pi over 4, or I can go all the way around here, like Annika gave me, and I can do the 7 pi over 4. And they're both right. It doesn't matter which one you pick. They'll both be correct. So take your favorite. I'll do the 7 pi over 4 this time. And we go from there. If you had chosen the negative 3 square root 2, what would have happened up here instead is that you would have started out by going left. Hang on. That wasn't what I was trying to do. Forget it. Okay, I'll just use a different color. So you would have started out by going left 3 square root of 2 like this. and then we would have had a swing around here, and so at that point it would have been the 3 pi over 4. So if we decide to go negative, it will affect the angle measure that we pick, but we still have ability to make different choices, just like with this one, we could have chosen 7 pi over 4 or negative pi over 4. Because those are coordinates. Coordinates are not the only thing that we change the system that we're in on. We also do it for equations in general. So we're going to do a couple of equations. So again, we're going to convert, and we're going to go rectangular now into cylindrical. So that's like what we just did. It's just that we're going to do it for an equation. So our equation is z equals x squared plus y squared minus 11. So using the same items that we did before, do you see a natural exchange that we could make to put this in the right system? So remember, my cylindrical coordinate system is not going to have x and y. It's going to have r, theta, and z. So the z that's here is good, and I don't need to change it out. But I've somehow got to eliminate the x and the y. Yeah, x squared plus y squared is actually r squared. So I can simply make the switch of the x squared plus y squared, replace it with r squared, and I'm done. So these are not all involved, right? Some of them are very straightforward and simple, just swaps to make. Let's do the other one. We can probably fit it in right here. And we're going to convert and go the other direction. So we're going to go from cylindrical into rectangular. And we are going to have the equation r equals 1/2 z. Now, this one's not quite as straightforward as the last one. It's okay. We do have a z. That's okay. But I don't want there to be an r. I need to swap it out for something. And if you take a look back, you have 3 different equations that involve r. You have, 2 different equations. I meant to say that. No, 3. There are 3 different equations that involve r. You have one of them that's written like this, right? We could solve this for r and we could use it. And we could do that with this one as well. The problem is that if we use those, then we're going to insert into the system theta, and I don't want theta in my problem. I want specifically to eliminate the r's and the thetas. So the third option, which is a better choice at this point, would be to use this one because it does eliminate or have the ability to eliminate the r and introduce the x squared and y squared. The problem is that, of course, this equation as it is written in terms of r squared. Now, if you wish, you can square root and you can do that and use that equation. That's okay. But it's also fairly friendly just to square both sides. So if I were to square both sides here like this, then I'd be able to replace the the r squared with the x squared plus y squared. Again, it's not the only way to doing it, but it's kind of a nice one. Not only that, but at this point, we could manipulate it and turn it into a very familiar equation. And in fact, that's part of my directions that I forgot to write down. We're going to sketch the graph. I say familiar, at least I hope that it's a little bit familiar. We did do it last time. We can change this so that it's x squared plus y squared minus 1, well, we wrote them this way, z squared over 4 equals 0. It is an elliptic cone. So the elliptic cone, if you'll remember, looks like, an ice cream cone, like, the cones you get at the store, not with the ice cream on top of it, but where the top of it could be at an oval shape. It didn't have to be a circular shape. So it looks something like this. And it opens both upward and downward. So I've got an elliptic cone. We should mark at least the axis that we're rotating it around. And what would that axis be here? Z, because it's the negative one. Yeah.
And on the test, are you going to want us to have like specific points marked on these? Like
No, we're not going to get that specific. It's a sketch. Yeah, we're just looking for the basic sketch. Okay, we're about to change systems into a system we haven't encountered before. You ready?
What's the elliptic cone? How do you decide whether it's just one part or
It has to do with whether or not the equation eliminates you being able to have it. Like, looking at this one, the value for z can be positive and negative as the equation was originally given. There's nothing that prevents that. You're thinking of one that we did before where it started out with a square root already in the problem, and this one doesn't have that. If we were to put the square root in the problem, we would be inserting the square root into the problem, and then we would have the ability to still have the positives and the negatives. Okay, so the location or the time when we had only the top part was because it started out having a square root in the problem, which meant the principal square root. That's a good question. Okay, what was the other half of the title of our directions for today, or title for our section today? Yes, that's right. So we're now going to talk about the spherical system. Okay, so think about what we've done with polar coordinates. With polar coordinates, like in 2 dimensions back in chapter 10, we measured the distance away from the origin, then we measured this rotating feature, right? And what we've done to create cylindrical coordinates is after we rotate it, we just pushed it up in the air, pushed it down, right? Well, another option is to do this sort of idea where we do the distance out from the origin. It's done in a little bit different way, but we're measuring the rotating distance around the XY plane, and then we're measuring the rotating distance up in space instead of the straight vertical up and down distance. That's the right idea you should have in mind as you're looking at this. So we're going to look at a point P, and it's represented by and we don't use R, okay? We're using rho. So rho looks kind of like a P with a curly tail. That's what I think it looks like anyway. We're using theta, okay? And it is the same theta. The theta is exactly the same theta from the other coordinate system. And then the last one is phi. And in math we say phi. Some other places you'll hear it say phi. And if you see it written, it looks usually like this. But if you see it typed, it looks like this. And I don't really have any idea why there's the difference, but I just want you to be aware that when you see it printed like in WebAssign or on a book or something like that, that's the same thing. But if you want to write it like that, that's fine. I like the way that we normally do write it, the one I drew, because it's almost like writing cursive, right? I can just swoop it out and I don't have to pick up my pen to do it. But yeah, if you wrote it that way, that would be just fine. So a couple things then about these coordinates. So rho is the distance to the origin, but it's not the distance in the XY plane. It's actually the distance in 3 space. So it's the distance from P to the origin. And unlike R as well, that rho value really is going to be positive or 0. We're not going to do any negatives like we did with R. The second one, theta. Theta is the same angle as in cylindrical. Provided that R is greater than or equal to 0. So as long as the R value is positive, it's the theta is associated with that R value. And then the last one, phi. So phi is the angle between the positive z-axis, positive z-axis and the line segment OP, so O being the origin, P being our point in space, and phi will be between 0 and pi. So we need some conversions to be able to work with this as well. So we're going to do spherical to rectangular first. So spherical to rectangular, x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And Z is equal to rho cosine phi. Note card, right, Hannah? Yes, absolutely. Okay, let's write the other ones down. If we're going from rectangular into spherical, rho squared is x squared plus y squared plus z squared. Tangent theta is y over x. That should look familiar. And then phi is the arc cosine of z over the square root of x squared plus y squared plus z squared. And while it is in fact true that that denominator right there is rho, we don't usually intermix our notation that way, right? Rho and phi and theta are trying to be ascribed in terms of the other variables. That's why you're seeing that happen. But if you've already found rho, you should be able to use it in that location just fine. So we're going to do some conversions. I think, let me put these on the next screen just so that we have them as a reference point. Okay, so example, we're on 5. We're going to convert, and we're going to go from rectangular into spherical. And our ordered triple is 2, 2, 4 square root 2. So that's x, y, z. So while you don't have to do this, I do tend to start putting these in the more coordinate systems that we're in just to remind myself what I'm given and where I'm going from. So my x, my y, and my z are the 2, 2, and 4 square root 2. So I'm looking to put things into rho, theta, and phi. Let's start with rho. Well, rho squared is equal to x squared, so that's 2 squared, plus y squared, another 2 squared, and z squared, which is 4 square root of 2 squared. So these are, of course, 4. What is 4 square root of 2 squared? 32. If we add all these pieces together, we get 40. So rho, would be square root of 40. And if simplified, what would I get? 2 radical 10. So actually, let me just put it over here as to what I'm getting as my answer. So we've got 2 square root 10. Okay, is that okay so far? We don't get any freebies like we did with the cylindrical and the rectangular, by the way, so we actually have to calculate them all. So that's rho. How am I going to find theta? Well, tangent theta is equal to y over x. That's 1. So what tangent value, we already did this once today, or similar, we did similar, we got to have -1 actually, but what tangent value gives us, or what angle value gives us a tangent of 1? I mean, remember, it means that sine and cosine are the same, that x and y are the same, pi over 4. Yep. So this is pi over 4. So I've got pi over 4. And then we have phi. So phi will be the arc cosine of z, which was 4 square root 2, over rho, actually, which we had found before as 2 square root 10. Well, as anticipated, you're probably not going to get a lovely value in there because I do have a square root of 5 showing up. If you want to simplify it a little bit, it's not a bad idea before you enter it in your calculator. If you were to enter it in your calculator at this point, it wouldn't be the worst thing you could have ever done. So if I simplify the 4's here, I'm going to get a 2 on top. I can actually simplify the 2 with one of these 2's here as well. So at the very least, you might want to write this as 2 over square root 5. If you want, you could also write it as 2 square root 5 over 5. It doesn't really matter because you're going to have to use your calculator either way to find it. So go ahead and grab your calculator and let's find out what is the arc cosine. We'll go with 3 decimal places, but just use whatever they ask you to do when you're working your homework. We'll do 3 when we're working together. 3 decimal places for the arc cosine of 2 square root 5 over 5, or 2 over square root 5. What'd you have? 464? Oops. Okay, so that would be our phi value. So our solution would be here.
Tangent theta, how do you know if it's pi over 4 or 5 pi over 4?
Say again?
And how do you know if it's pi over 4 or 5 pi over 4? Does it matter?
5 pi over 4? Oh, you mean your angle measurement as you're measuring around there. So we're going to be using, well, you can actually tell it from the coordinate you're in. We're in X and Y.
Mm-hmm.
So in that coordinate, we're in quadrant 1. That's probably your easiest way to tell why it would be pi over 4 as opposed to 5 pi over 4. Yeah, you're right. We should have checked that. I didn't think to. Okay, let's try the other one. Going the other direction. So we're going to go from spherical into rectangular. And our ordered triple is 12, 3 pi over 4, and pi over 9. I probably should have done that again here. It would be helpful. Okay, so we've got that same system at the top. And we're working with spherical into rectangular. So looking at the spherical into rectangular, we have definitions exactly for x equals, y equals, and z equals. So x equals rho, which is 12, sine of phi, which is my pi over 9, and then cosine of theta, which is 3 pi over 4. If it weren't a pi over 9 and you had the 3 pi over 4, I'd say let's just do this, you can circle by hand, keep it exact. But once you see that pi over 9, you know there's not going to be a chance for you to be able to do that. So you might as well let your calculator do all the simplification because you're going to have to at some point do so anyway. So what is the angle, or not angle, the value for x? Again, we're just going to use 3 decimal places for everything we're working with on these.
-2.902.
Okay, good. Okay, so that's x. I'm moving as we go, so let's put that over here. So I have -2.902. And then we're going to do y. So y is equal to rho, which is 12. Same angles in the same order. It's just the sine of pi over 9 and then the sine of 3 pi over 4.
What do you know?
What'd you get?
Same thing, but positive.
Yeah, it's 2.902. And the last one, z. So z is rho, 12. And then the cosine of phi, and phi was the pi over 9. So what is 12 cosine pi over 9?
11.276.
Yep. So this would be our ordered triple. Okay, any questions? Okay, the next two are to change our equations from one to the other. So we're going to do rectangular to spherical. And our equation we're going to be working with is x squared plus y squared minus 3z squared equals 0. Rho squared looks similar to what I have at the beginning of this. I mean, the x squared plus the y squared look good, but I don't have plus z squared. But man, if I did, it'd be kind of nice, wouldn't it? So we're going to. We're actually going to just put in the z squared. So I have x squared plus y squared plus z squared. You can't just, of course, add that in there without compensating, so we will add the z squared to the other side. So in the interim, right, in part of what I'm doing, I'm going to have some mixed notation. That's okay. We'll get to it and we'll fix it. So this is a rho squared right now. And while I do that, I'm going to go ahead and move the z squared to the other side. That's the leftover piece, so I have 4z squared over here. So it's mixed notation. That's okay, because we're going to replace it because we know an equation for z. So the 4 will stay. Z is rho cosine of phi, and that would then be squared. Now technically we have put it into a form that that matches the description. It's in spherical coordinates now, but kind of like when you have a line and you're trying to give an equation for a line at the end, you want it in a simplified version. We're going to simplify this out a little bit too. Okay, so what does this look like? Well, take a look. I've got rho squared equals, I have my 4, and then I've got now rho squared cosine squared of phi. There's a rho squared on both sides, so I can eliminate it by dividing out by it. So I can eliminate the rho squared. So I have 1 equals 4 cosine squared of phi. Or we can say the cosine squared of phi equals 1/4. And we can very nicely square root this to say that this is the cosine of phi equaling what? 1/2. But there's just one variable there, isn't there? Where is the cosine equal to 1/2? It's unit circle stuff. What angle measure? Pi over 3. Yeah, it's at pi over 3. Yeah, or 5 pi over 3. So we can go back to the original one to check it out. It will be at pi over 3. So this is our final and most simplified version of the equation. It's actually the angle measure equal to a constant.
Will it always do that?
No. Let's do another one to show you that they won't, in fact. So we're going to go from spherical into rectangular and sketch. So spherical into rectangular, I had my equation is rho equals 4 cosine of phi. So there's an equation that said that z is equal to, rho cosine phi, like this. And if we take a look at that and we solve for the cosine of phi, we can see that z over rho is equal to cosine of phi, right? So I'm going to replace the cosine of phi with z over rho. And then I can multiply the rho to the other side. So this is rho squared equals 4z. What is rho squared? X squared plus y squared plus z squared equals 4z. That's somewhat simplified, but it's not in a very usable form, or at least not very convenient. it would be cleaner, it'd be better if I moved that z over. And we did a little completing the square to put it into a form that's familiar. I can add a 4 to both sides. And I would have x squared plus y squared plus z minus 2 squared equals 4. Do you know what that's an equation of? It is, but it's a very special ellipsoid. It's actually a sphere. It's actually a sphere, yeah. How do I know it's a sphere and not just an ellipsoid in general?
Because the A, B, and C values are all.
Yeah, the coefficients of x squared, y squared, and z squared are all 1. So generally speaking, it is an ellipsoid, but really specifically, it's a sphere. So this is a sphere of radius what? Yeah, with radius 2. Where is it centered?
0,
Centered at 0, 0, 2. And if we were to draw it, because it did say to sketch, it's not too bad of one to draw. It's centered at 2 up here like this, but it has a radius of 2. So what that means, oh my goodness, that was way too thick. What that means is that it's very much like this, because it's going to hit the origin and it's going to go like that. So we have something like that going on in a visual. Okay, so here's what I'm going to do. I'm going to give you the, I think I'm just going to give you the homework. The last piece, let me just tell you what it is so you'll know where to pick up, and I'll try to specify when I post the video, start at this, this particular time frame. It's going to be going between the two coordinate systems we haven't gone between, which would be spherical and cylindrical. Okay, so technically, could you always go through rectangular to do that? Well, sure, you could, but that seems like a lot of work. If there's a way to do it directly, that would be less work. So make sure you're writing down this homework, because this homework, when it posts on the old video, will not make sense. It will not be the same. This homework is page 813, and it is long. I'm warning you right now, it is long, but I'm also going to let you know I'm picking it up. Okay, so it is worth your time to do it. It is long, but a lot of these are really quick. I mean, we did 8 problems in 40 minutes or so actually together, including all my descriptions of what we're doing. So it's not terribly bad. So 4, 7, 11, 14, 16, 17, 20, 24, 25, 28, 32, 35, 37, 40, 44, 45. I'm not done. 47, 52, 53, 56. It's a lot. 60, 61, 64, 65, 68, 69. Are you still breathing? 80, 83, and 86. They go quick. I promise they go quick. And it also means that your web assign's brief, right? All right.
Sure.
Sure. Sure.
It's even worse when it's